Since we are slightly late, and I'm sure Nutan has a lot of content that you would like to present, so we can try to move partially the discussions at the end of this block and keep a little bit less discussion during the presentation.
Yeah, thanks. The next point I would like to just make is I already presented what VP-VNP is. What I would like to say is that these questions about lower bounds, which are about VP and VNP, etc., or any other lower bound questions, they typically have close connections to algorithmic questions as well. And a specific algorithmic question that I'm thinking about is
signal down.
Yeah. And then
we lost you for maybe 10 seconds.
Oh,
15.
Again, or now? Now it's okay?
Now it's okay.
Yeah. So equality of polynomials and polynomial identity testing, 2 questions. So what happens here is there are 2 polynomials in the polynomial equality testing. They're sitting in a black box. And I get an input x, and I query the polynomial at input x. And what this gives me is whether they are equal or not. So it kind of computes the difference between the two. And if the difference is 0, then it's just 0. And if it's non-zero, then it gives the value that is the difference between these two. Okay, so that's the output I get. And I want to figure out by asking as few questions as possible to this black box, whether the 2 polynomials are identical or not. A similar question is with just 1 polynomial. You get, again, black box access to this polynomial. It keeps giving you evaluations of this polynomial as the output, this black box. And you want to check whether the polynomial is identically 0 polynomial or not. Now, anybody who has seen something similar would immediately guess that the 2 problems are actually just related to one another. Because I can take f of x to be h of x minus g of x, and then the problems are just the same, right? So that's not a big deal. The 2 problems are just related. Sometimes equality of polynomials is a more natural question for some people, so I thought I should just mention it here. But polynomial identity question is just like a generalization of this question. All right. And there is a very simple randomized algorithm to solve this polynomial identity question. It says, pick a random point, query the black box at this random point. If the output is 0, say the polynomial itself is 0. If the output is non-zero, then say the polynomial is non-zero. Just one query, just one randomized query. This is an efficient algorithm, very clearly. It uses some randomness, but other than that, it's quite efficient. And its correctness is very easy to argue about because, you know, if you just look at a univariate polynomial, we know that if the polynomial is 0, of course, wherever you query it, it will be 0. But if it's non-zero, then there are like these, there are at most d plus 1 points where this polynomial is going to be 0. If the polynomial itself is non-zero, then it only can have at most d plus 1 roots. Yeah, order d roots, let me say, at most order d roots. So as a result of that, a non-zero polynomial will evaluate to 0 on very few points. So this randomized test will succeed with pretty good probability. Okay. So this can be mathematical.
I have a question about this, the domain of x. You pick x uniformly at random, but from which set?
Good point. Very good point. So it depends on what kind of polynomial we are looking at, because I said that our polynomials are over this complex field. It really boils down to we put really good constants here because now, you know, the efficiency, etc. matters. It turns out that if the degree is d, Then over complexes, you can pick even first, like you can pick just integer values, random values, even among small integers, and this test will work pretty well. So that's something that can be easily, not easily, but it's known. And in general, if we are working over finite fields or something, then there are versions of the statement which hold over finite fields as well. Even small fields like characteristic 2 and so on, there are statements which show this. So this is a statement that is very well studied. It's known under many names. One of that is Schwartz-Zippel lemma. Then there is, so there is a long history to this. The point about saying this is that the above algorithm is randomized, and can we de-randomize it is another very well-studied problem. Okay, so I'm using these things to say that what are the important problems, and this is yet another important problem that people have studied in algebraic complexity theory. So the previous problem, the VP versus VNP problem, is a lower bounds problem, because we want to show that something is not computable efficiently. And this is an upper bound, or algorithm problem, where we want to show things are computable easily. So the problems are kind of a different nature. And what's known by a result of Cabanets and Impagliazzo is that these two are actually formally connected. So what they proved in 2004 is that if you are able to prove the lower bound, if you are able to solve the lower bound question and show it in the negative, that is VP is indeed not equal to VNP, then you would have also given a deterministic algorithm for this problem. It's a very strange kind of a statement to make, actually. But this theme comes up again and again. So you may have heard this result. I don't know what Ryan Williams spoke about earlier, but he has this theme that he's developed since 2010, where again he says that, oh, if you can come up with better than brute force, algorithms for satisfiability in certain models, having lower bounds for that models is useful. And so connections of those sort are known in other situations as well, and so are here. And so the question is, basically what I'm trying to say is, it is quite interesting to solve this problem. So just because it relates to P versus NP question, and that's one interesting reason. Other interesting reasons could be it implies something for algorithmic questions such as this. And this question of polynomial identities comes up naturally in many situations, like checking whether the two automata are equivalent or not. This can be formalized as a polynomial identity question. In fact, Sipser in his book also mentions that, and the basic automata theory book that Sipser has, and so on. So a lot of problems of model equivalence of models, or equivalence of models of different models of computation, can be framed as polynomial identity questions by just giving, every unit operation inside it a variable, and then writing a polynomial out of it, and then saying that, oh, if these two polynomials are equal, then in fact the two models are equal, and things like that. So polynomial identity question does come up naturally in many situations in computer science. And what this says is that you will be able to give efficient efficient deterministic algorithms for it if you prove lower bounds. Okay, so now the question is about what lower bounds do we know? And turns out we don't know so much. But we do know something in restricted models of computation. And therefore, I would like to introduce some restricted models of computation to you. So there is a lot of text here. So let me just scroll a little bit for now. These are polynomials. Okay, homogeneous polynomials are polynomials where every monomial has the same degree. This is something all of us already know, perhaps. Multilinear polynomials are polynomials where every variable appears at most once in each monomial. This is also something we probably already know. Set multilinear, maybe not so well known, but here it's multilinear with respect to some set partition. That's what set multilinear is. So you have a partition of variables x1 to xt, and every monomial has exactly one variable from every set. So if we were to go back and look at our examples, then, this one is not homogeneous because it has all sorts of sets of different sizes and then monomials corresponding to degree 0, 1, 2, etc. So this is not homogeneous, but this is a homogeneous polynomial, but it's not exactly set multilinear. There is no nice set, but it is also multilinear. So every variable occurs at most once in every monomial.
I think it is set multilinear if you can just take the singleton sets.
Yeah, but yeah.
I know it's ridiculous, but it is.
Yes, you're right. For if we take every variable as its own set, then probably many polynomials will also be set multilinear. That's probably true. Well, no, actually, I take that back, right? So what set multilinear requires is every variable. So there is exactly one variable per set. So let me go back to the definition of set multilinear. Set multilinear is a little more restrictive than multilinear. In that, every monomial has exactly one variable from every set. So now, if you put singleton variables per set, then the only set multilinear polynomial is the single monomial that multiplies all of them. So that's not quite true. But okay, but let's look at iterated matrix multiplication. This is clearly set multilinear as well, because the sets are this, and so on. So I actually defined it because I'm going to use set multilinear. So there's no surprise there. It is not very difficult to see that determinant and permanent can be thought of as set multilinear if the sets of variables are your row elements or just column elements. So if you define your partition of variables as row variables every row forms one set of variables, then with respect to that, determinant is set multilinear, it's homogeneous, it's multilinear, etc. Similarly for permanent. Okay. And then for every model of every polynomial, there is corresponding model of computation that you can define. For example, a homogeneous polynomial, a homogeneous model of computation is where every gate, that is every plus and multiply operation, computes a homogeneous polynomial. Similarly multilinear and similarly set multilinear. So you can have restricted models of computation computing restricted models of polynomials. Of course, if the polynomial is inhomogeneous, then homogeneous circuits just cannot compute it. So it's not a model that allows for such computation. So that's a no-brainer, but it is possible that a homogeneous polynomial is computable by an inhomogeneous model of computation. That is possible. In fact, we just did that. If you look at this is an inhomogeneous model of computation because, it has this particular model is inhomogeneous because this variable t is going to vanish and it's going to become a constant here. So then this computation here is going to look like product of some alpha plus xi. Now this is an inhomogeneous gate already. This multiplication gate is already an inhomogeneous gate because it's multiplying things which are themselves inhomogeneous. But eventually, after interpolation, appropriate substitutions of beta, what it is computing is a homogeneous polynomial. So it can happen that a homogeneous polynomial is efficiently computable by an inhomogeneous object. And sometimes that's the whole fun of quick computations, right? And then there are statements which say that actually some of these models are very easily related to one another. So here is one such statement. Let's say P is a polynomial that is homogeneous already, and it's being computed by an arbitrary circuit of size poly n. then I claim that, in fact, P itself can be computed by a more structured, namely homogeneous circuit, without too much blow up in size. So this was polynomial, but now it's going to be polynomial in n as well as the degree of the polynomial, which is d. And this is not very difficult to see actually. So to homogenize, given a circuit that is computing a polynomial that is homogeneous, but by itself it's not homogeneous, then I can convert it into one which is homogeneous. How do I do that? Take the circuit which is inhomogeneous. It has lots of gates. For every gate, make d plus 1 copies of that gate. The idea is going to be, we club together monomials of the same degree in this copy. So in this copy, I collect together all monomials that reach G and are of degree I. Because G is an inhomogeneous gate, it is computing monomials of degree 0, 1, 2, etc. So I just kind of try to, propagate them component by component. That's the idea. And it can be done quite easily. For example, suppose we have a plus gate in the original inhomogeneous circuit with G1 and G2 as its two children. Then inductively, let's assume I have collected together the degree I components of G1 and degree I components of G2. Then degree I component of G is just by adding these two. It's not much to do. How about multiplication? If I have G1 and G2 and they multiply to give G, then to compute the degree I component of G, I basically have to look at all possible ways of getting degree I from G1 and G2. So let's say take degree 1 component of G1 and degree I minus 1 component of G2. They could perhaps multiply and give a degree I component in G. Similarly, degree 2 component of G1 and degree I minus 2 component of G2, and so on. So you can convert this circuitry into this one. And now note that every gate here is homogeneous because in fact it is computing degree, that degree component which it has, which it is labeled with by construction. So then this sort of a statement is sort of interesting because what does it say? On the one hand, it says, give me any polynomial size circuit. I can make it homogeneous by not spending too much operations. But if I read this in contrapositive, if I just look at the contrapositive of this, it says, if you can prove superpolynomial lower bounds for homogeneous circuits, then they imply superpolynomial lower bound for general circuits. So such statements, which are efficient conversion statements, can be leveraged to prove lower bounds by saying, oh, just prove lower bound for this class. Don't worry about this general class, which looks, it's less structured, it's hard to think about. Let's think about homogeneous, which is maybe easier to think about. And because I know that there is this conversion sitting there, eventually, once I have a lower bound for this class, I'll get a lower bound for this class. So these are called escalation results. And they have this property that from general model, you go to a special model without too much blow up. Then lower bound for a special model implies lower bound for general models. Yeah. And finally, actually, this is right now not so important for us. I will change my slide deck to the other one. So this was the part 1 actually, which we went on for quite some time. But I think it's good that we spend some time on this because now the next part is going to become quite easy. So I'm going to change the slide deck a bit. If we want to take like 2-3 minutes break, I'm fine with that as well, or some questions also.
So I have a short question.
Yes.
So how VP versus NP compares to P versus NP? Does one imply the other?
Yes, indeed. If we are able to show, I actually have a slide for that. If we,
Okay.
if we can, is that okay if I just do it then?
Sure, sure.
Is it still visible? Like what I'm.
Visible full screen. And with regard to time management, we have half an hour to finish this second session.
Okay. So should I just start in that case?
Yes, please.
Yeah. So now this is more about the work we have. So this is a joint result with Shrikant Srinivasan, who's at Aarhus University, and Sebastian Tavanas, who's at Lama. And how do I move? Yeah. So we all know this part now. A lot of the slides are going to become quite easy, but I want to keep them because they put everything in the context again. And maybe some things I did not quite define, which will come up. So a polynomial is just any polynomial. For us, field is complexes. And here is a kind of a picture. And we've been talking about size, which is the number of operations. But another thing which is of interest also is the depth.
Sorry, I interrupt, Nutan. Is there a problem with using the rationals, say, for the field? Because for the rationals, we have finite representations in standard computation, whereas for the complex numbers, we don't.
Yeah. You can use any field. Polynomials can be defined over any field. That's no problem at all. It's only
it's okay with all the things that come if f is the same as the rationals q.
So there will be one place where we need characteristic 0. Q is still okay, but we need that. But other than that, really,
It's okay. I mean,
everything I say will hold for all fields, really. So it's not so important.
yeah, finite fields may be different, so.
Yeah.
Okay.
Thanks. And so I talked about circuits. I didn't quite mention formulas. We will not talk so much about them, but formulas are just, like these circuits, except this underlying thing looks like a tree. It's not going to come up too often, so that's why I didn't speak about it. This is an example we already saw. And so I will not repeat it here. And now to the question of that we just were going to talk about. So it is formally known by a result of Bergeser, I should have put a reference here, that in fact P versus NP, so VP versus VNP could be a stepping stone towards P versus NP. It's not to say that this is the only way to prove P versus NP, but it is known that algebraic circuit lower bounds formally are easier than Boolean circuit lower bounds. So in particular, if Boolean circuit lower bounds hold, then algebraic lower bounds also hold. Does that answer the question? Great, thanks. And now a little bit about constant depth circuits. So this talk is going to be about constant depth circuits. And I want to tell you a little bit about them. That was also there in my notes, but I think I'll do it over here. Constant depth circuits are quite powerful objects of computation. We saw that iterated matrix multiplication, though there is like a log depth representation for it. Initially, we said that there's a long representation for it. Then we said there is a log depth representation for it. And then we said there's constant depth representation for it. And a similar thing is known for all polynomials in VP, actually. Okay, so let P be a polynomial on n variables of degree d and of size polynomial in these two parameters, P and D. Then it is known that not just for IMM, for any such polynomial, it can be computed by this depth 4 circuit of size n to the order square root d. So we saw how to do it for IMM. That was a special case, but this is known for all polynomials in VP. In fact, so this is a line of work, Agrawal, Vinay, Koran, and Thavinas showed this. In fact, if we now look at characteristic 0, then we don't even need to stop with depth 3 or depth 4. We can even go to depth 3 circuits while keeping the size exactly the same. It's a very surprising, very beautiful result by Gupta, Kamath, Kayal, and Saptarshi, and then Thavinas. So what this says in our world of escalation is that proving lower bounds for constant depth circuits is enough. So just to put it in the context of this escalation I talked about, the result we saw on the previous slide says that every polynomial in BP has a depth 3 circuit of this size. What we don't know is this statement, that there exists a polynomial in B and P such that any depth 3 circuit for it has strictly larger size than n to the omega square root t. So it's n to the little omega square root t. This is open. But if somebody is able to prove this, just give a polynomial in B and P for which there are no depth 3 circuits of this size, then we would have separated VP from B and P. Yeah. Unfortunately, we don't know this. So what do we know? Yeah, so what I'm trying to say here is depth bounded circuits are a good place to start because they already can give strong results. Yes? Okay.
Is it me? Yeah, I just wanted to make something a bit clearer. D is a polynomial in N, isn't it? Like the degree of the polynomial is a polynomial in N, right?
No, degree is a separate parameter here.
Oh, here it's separate.
Yeah.
Okay.
Even all along, we've been thinking of D as a possibly separate parameter. In determinant and permanent, it has to be N if the matrices are N cross N. But for iterated matrix multiplication, for instance, N and D could be sort of different parameters.
Okay, I
So
thought this is what we constrained to be polynomial in the definition of VP and DNP.
Yeah, as long as D is small, it's all okay. So D shouldn't be exponential in N.
Yeah, but
But-
already if it's polynomial, here we have a circuit of size n to the poly in n. So it's an exponential circuit.
Yeah, yeah. So here,
Okay.
here D equal to polynomial is not so interesting, but D way smaller than polynomial is actually interesting. So suppose D is like log n. So then D is not exactly omega poly n, but it's like little o of poly n. It's log n. And
Mhm.
here actually then it's really interesting. Yeah. So it is still bounded by polynomial in n, but it could be asymptotically way smaller than it.
Okay.
And then this bound is sort of interesting.
So just you mentioned the determinant and permanent as an example, and you said D is N, but actually D there, the degree is the square root of the number of variables.
Yeah.
Right.
N and little n are hard to say when we are speaking.
Yeah, but what I mean is so already it's non-trivial upper bound to say effectively the number of variables to the fourth root of the number of variables, which is the upper bound you have over here.
Exactly. Yeah.
And it's quite conceivable that for the permanent you could show that depth 3 circuits. I mean, one wouldn't expect them to be that small.
Yeah, absolutely. You are absolutely right. Yeah. So this should be, I mean, this statement should really be true, right? So yeah. Okay. So what do we know then? Like now I tried to kind of sell to you that constant depth circuits are interesting because my result is about constant depth circuits. So I have to sell that model to you. So I hope it is somewhat interesting. But what do we know? So in the Boolean world, by these results from the 80s by Aitoy and Fuchs, Sachs, Sipser, Hostad, Rasbro, Smolensky, we have really tight lower bounds for constant depth Boolean circuits. In the algebraic world, however, the picture is not so rosy. If we just look at sigma pi circuits or formulas, I should not call this formulas, circuits, then really proving lower bounds is trivial because, you know, in depth 2, you need the size of the circuit to be at least as much as the number of monomials in the polynomial. There is no escape from that because you just have depth 2. So all you can do is sum of monomials. Every polynomial can of course be written this way, but then its representation is as expensive as there are number of monomials in that polynomial. So the lower bound is just the number of monomials in the polynomial. And then we saw very, very simple polynomials which have lots of monomials. So they have to have a large sigma pi circuits. But as soon as you go to depth 3, even prior to our result, what was known was in 2016, Kayal, Saha, and Tavenas showed almost cubic lower bounds for these polynomials. So they showed that there is a polynomial which can't be computed using sigma pi sigma circuits of size smaller than this. Later, this result was improved for depth 4 by Gupta, Saha, and Tanke in 2020 to give an n to the 2.5 lower bound. And if you look at depth more than 4, 5 and above, then only superlinear lower bounds were known. So now I can present the lower bound we have. So what we are able to show is that there are parameters n, d, and delta. And there are some constraints on these parameters, but that's less important. We are able to say that there is a polynomial which we can really write down very easily of degree d, such that any algebraic circuit of depth delta, computing it, has size n to the d to the inverse exponential in delta. So don't worry so much about this inverse exponential business here. Oops, what is this? Yeah, don't worry so much about this inverse exponential business, but just think of it as it's a function that grows with n as d in the exponent of it. Okay, I'll make this more clear. So first, let me tell you what that hard polynomial is, the explicit polynomial. It is our friend iterated matrix multiplication polynomial, which we already know. Okay, this is how we defined it. It is this polynomial with respect to which we are able to prove our lower bound. So then, what are we able to say? We are able to say that any algebraic circuit of depth delta computing IMM must have this size. Recall that from our upper bound, we were able to say that any depth delta circuit for IMM must have size n to the d to the 1 by delta. Has an upper bound of this size, right? This divide and conquer like argument showed us this for depth delta. And this says that you need something like n to the d to the, say, what shall I say, 1 by 2 to the delta or something like this. This is a lower bound. So we are able to say that this much is necessary, and we know from our construction of divide and conquer that this is sufficient. Okay, so this is still a little weird, maybe. Clear drawings, stop, annotate, and yeah. But let's look at exactly depth 3. At depth 3, we get a really strong lower bound, actually. We are able to say that whatever depth reduction gives is the best you can do. So for larger depths, this, because there is an inverse exponential dependence on delta, We are not getting tight lower bounds for higher delta. That's an open question we would like to answer. But at depth equal to 3, so sigma pi sigma circuits, we are able to show that to compute this IMM polynomial, you do require n to the omega square root d size. The depth reduction tells us that this much is required, this much is sufficient, and we are able to say that this is required. One more slide which elaborates on this. Let's recall what our goal is. Our goal is to separate VP from VNP. We want to show a statement like this one. What we are able to show is this one. So we are able to say that there is a polynomial in VP. IMM is very much a polynomial in VP. Unfortunately, it's not in VNP. To separate VP from VNP, we need something here which is not here. That's not what we get. We get that there is a polynomial in VP such that any depth 3 circuit computing it must have this size. So there are two places where we fall short. Our polynomial, the hard polynomial, is hard with respect to the right kind of model. Yeah, this is the model we want to defeat. So there we are good. But our polynomial, unfortunately, is in VP. We want it to be in VNP. Okay. And also the quality of our lower bound over here is n to the omega square root d. Of course, because this is IMM that we are doing with respect to, we cannot hope to prove a better lower bound. But really, to separate VP from VNP, we need little omega square root d. But there is, I feel there is hope, because our lower bound could be thought of as proof of concept. And now maybe one comes up with a polynomial, say f prime, which is in VNP. So we kind of made it a little more complicated. And then maybe parts of our proof techniques, we are able to even lift the lower bound from big omega square root d to little omega square root d. It is imaginable. So this is where we are. And this is the first superpolynomial lower bound, as I mentioned earlier. So prior to this, the lower bounds known were n to the 3 or n to the 2.5. So the n to the some fixed constant. Whereas now for us, it's n to the d to the inverse exponential in delta. So it's like something that grows with d. So in that sense, it's a superpolynomial lower bound. Right. So this is one result we have. And the second result we have is about the polynomial identity testing question I told you about. And this is something we already talked about, right? Just like this statement of Cabanets and Impagliazzo, which says that if you are able to separate VP from VNP, then polynomial identity testing question has efficient algorithms. There is a constant depth version of the same statement known. So what does it say? If you are able to separate constant depth circuits, if you are able to show hardness for constant depth circuits, then you will be able to solve polynomial identity testing question for this class of circuits efficiently. Maybe it's a bit of a mouthful. Let me repeat. If Cabanets and Impagliazzo say that if you are able to show that there is a hard polynomial not computable by general circuits, general VP, then the polynomial identity testing question for that class, in this case general VP circuits, becomes easy. And a constant depth version of this, which was proved by Chow, Kumar, and Solomon, says that if you are able to show constant depth circuits are somehow weak, you are able to prove lower bound with respect to constant depth circuits, then polynomial identity question for that class of circuits, polynomials represented by that class of circuits, becomes easy. So this was already there, this was already known. And now we were able to prove the lower bound. We were able to prove the if part of the statement. We were able to show that there exists explicit small degree polynomials that are hard to compute for constant depth circuits. So overall, our result also implies that there is deterministic polynomial, deterministic algorithms for PIT for this class of circuits. If a polynomial is computable by constant depth circuits, then the PIT problem for them is solvable deterministically. Interestingly, this is a very well-studied problem, but prior to our work, the best known result for depth 3, for instance, was this one by Saxena and Sheshadri from 2012. They gave an n to the order k time algorithm for PIT for polynomials computable by circuits such as this one. These are circuits where not only do you have depth 3, but also the top gate has fan-in only k. Okay, and so for instance, if the top gate has fan-in 3, then they get n cube algorithms, but we only get sub-exponential time algorithms. But the top gate can have fan-in something like n or n square or something like this, in which case we get sub-exponential time algorithms, whereas they get exponential n to the n square time algorithms or something. So there are parameter regimes where our algorithm is better than theirs. Yes. So these are the two results we have. Yeah.
It just PIT of P means the input is another polynomial and we test it's equal to P.
Yeah, so the recall that PIT is like this black box thing. So this polynomial is sitting inside this box, and all you get are queries to this, and output is this evaluation of this. Now, by asking as few queries as possible to this black box, you want to check whether this polynomial is eventually 0 or not. And now when I say PIT for this class, it means I'm promised that what's inside this black box is certainly computable by this model.
All right, thank you.
Yeah, and because it's black box, I really don't know how it is computed. I don't get to look at the way the circuit is and so on. All I get to know is its evaluations. And PIT for a class just means, as I said, that the black box contains elements that are being computed in that class, and that's all. Yeah, sorry. Okay, and then there was one more statement we have, which is a depth hierarchy, which says that at every depth we have a separation. So let gamma be some depth and let S be some growing parameter, then we are able to come up with a polynomial Q gamma that has depth gamma size S circuits. But if you just allow depth 1 less than what it is computable by, say gamma -1, then already it must have super large size compared to the original. So we are able to separate every depth from every other depth, every consecutive depth. So this is like the, space hierarchy theorems or time hierarchy theorems that we prove in computation, that if you give me extra resources, there is provably more I can do, except here it is explicit. So I give you a specific polynomial for which we are able to do this. So that's all the results we have. So this is the set of results. So maybe we can again break and then I tell you a little bit about the proofs later.
It's a great moment to have a break. So in fact, we're slightly early, so I think we have some time, 2-3 minutes for 1 or 2 questions. Yeah, Mikael.
Come on, I have more than 1 and 2 questions at this point. So talking about the polynomial identity testing, just that, why is it? So you mentioned before that the separation between the classes holds by the existence of that family of random polynomials. So why isn't that enough for the PIT with sub-exponential time results that this random family exists, and that why do they require an explicit function?
Right, right. So that actually goes into this little bit into the theory of why that statement, Cabanet-Impagliazzo statement holds. So that statement vaguely says that VP not equal to VNP implies deterministic PIT, right? So this is the statement. And the way the statement is proved is that it's like we've seen such proofs in, say, cryptography. What cryptography says is that if one-way functions exist, then crypto, right? Or we've seen some similar things like in Ryan Williams's work, where you say that some lower bounds hold for a class of circuits, then there are fast algorithms for that class. Okay, so so this flavor is well known. Now in crypto, existence of one-way function. So in all of these, somehow, just existence of hardness is not enough to write down the algorithm here. So the algorithm sort of depends on this hard polynomial in an explicit way. So it uses this polynomial again and again in order to extract its hardness to come up with a fast algorithm. And therefore, to have your hands on that object is very important. So the thing that goes into this are called Nisan-Wigderson generators. And these generators are trying to, so in pseudo-randomness literature, so I'm throwing too many jargons here. So let me be very concrete. This is not helping. So let me be concrete. What happens here is you get so one thing I would like to just say is this statement is non-trivial to kind of prove. Okay, so that's one thing. But if I were to give the essence of what's going on, then the hard polynomial f that we may prove is used several times, again and again, by partially evaluating it and then feeding it into an object that so for PIT recall, we need a random string, which when queried at, the polynomial will be either 0 or 1. So I need that x, the random x I want to query. But I don't have, if I want to do PIT in deterministic way, I cannot afford to pick so many random coins. So the typical way to do this is to try to come up with this random x by using some sort of pseudo randomness. So instead of using pure randomness and to come up with this random query that we ask this black box, I actually use some hard function, and that hard function is then used to create pseudo-random bits. And then the pseudo-random bits are where you query this PIT. Now, how does one come up with the pseudo-random generator? It is by using this hard function. And now this hard function better be something I can use. So that's where I think the explicitness is useful. That's sort of unsatisfactory, but short answer.
Well, that helps. That helps.
Okay.
Thank you.
Yeah. Thanks.
May I ask a question?
Yeah.
So I'm interested in this sub-exponential time polynomial identity testing. So if you assume that the depth of your circuit is, say, d, what kind of sub-exponential time do you get more precisely? I'm asking because in parameterized complexity, we often have a situation where we can quite well understand, control the depth of the circuit. We write actually this polynomial explicitly, and we are interested in de-randomizing it. So what kind of sub-exponential time would you get?
So do you want this for the constant depth version? Can you just tell me what model you are considering?
Yeah, so suppose that yeah, P is computed by depth D circuit. And what kind of sub-exponential running time do you get for this randomization?
Yeah. So actually, you do get a reasonably good. So it is dependent sub-exponentially on the degree of the polynomial.
I see. So,
Yeah.
it will be something like n to power square root d.
Yeah, and the dependence on delta is going to be exponential in the depth. So the dependence on depth is exponential, but because your depth is constant, all those factors just become constants. So the sub-exponential is coming because of its dependence on the degree of the polynomial.
Aha, okay, so the degree, okay, so it would be like n to square root d, and there will be some factors depending on the delta, the depth of the circuit.
Yes. So
Okay.
the dependence on delta is like some constant to the some, like maybe, yeah, it's like x to the delta. I can forward you this paper of Kumar, Chow, Kumar and Solomon later. If you just drop me a mail, I will send you that, or you could look it up like Chow.
Yeah, so yeah, I will just look it up.
Yeah, Chow,
Yeah.
Kumar and Solomon.
Thanks. In our settings, typically we work over a finite fields of some finite characteristics, like say characteristic 2, which so this will not be immediately applicable, but
Yeah, there is some work people have done on finite fields as well, but I don't think this one will work there. Yeah.
Okay. Yeah, but still it would be inspiring to look for this.
Yes.
Yeah, thanks.
I add one short question, if I can. Is there a VNP, a natural VNP variant of IMM?
Not of IMM that I know of, no. But
Like
there is one
hiding some. Sorry.
Yeah, there is one which is called actually Nissan-Wigderson polynomials, and that is a good one for decoupling number of like n and d. It also has like these two parameters, so it's not a generalization of IMM. But I don't know of a nice generalization of IMM that is VNP complete. I don't know that. Yeah.
Thank you.
I have a question as well. And so you show lower bounds for some polynomials, some specific polynomials in VP against circuits of constant depth. So those circuits of constant depth are in particular in VP. They should do this thing in VP. So are there directions to show lower bounds for polynomials in VP by constant depth circuits with advice? That would be some constant depth fragment of VMP. Did people look at something like this?
Not in the algebraic setting. In the algebraic setting, I'm not sure how to formalize advice. It's a very good question, actually. Like I tried to think about it for a while. You could do it in some ways, but I don't know of any definite way of doing this, which is, yeah.
Okay, probably doesn't have relevance with respect to the complexity problems, but it seems like
no, yeah, it is.
if you try to find lower bound for something in VP, then you can allow even more powerful VP.
Yeah, you're right, absolutely. Yeah, I don't know how to do that. I tried to think about this advice model in the algebraic world. I don't know if there is a nice definition.
Are there any other questions from the audience? Okay, so maybe we can take a small break, and we're good on schedule. So I think we can take 10 minutes break, and then we'll start at, well, in 10 minutes. So we'll start 3 minutes before schedule, but so we will can expect extra time.
Great, thanks.